Ladies and gentlemen, welcome at this webinar series of large thermal heat storage. I see that a lot of people are just joining the seminar, so we just wait a few seconds before we start. Okay, let's start. Welcome to this first session of the large thermal heat storage. My name is Bas Godtkalk. I'm the International Business Manager of IF Technology, a consultant company in shallow and deep geothermal energy. And this webinar is supported by RVO, the Dutch RVO, and TKI Urban Energy, Top Sector Energy. Maybe to give you a little bit explanation about all the abbreviations. The IEEA is the Technology Collaboration Program from the International Energy Agency, focused on the energy storage. And within this program, we have a Task 39. And the Task 39 is a group of experts working on large thermal energy storage for district heating within this program. I just would like to start with a few guidelines for this webinar. We are very sorry, but we have disabled all the cameras and mics. If you have any question during the presentation, please feel free to drop your questions in the Q&A box, which is at the bottom of your screen. We have disabled the chat function, so please use the Q&A. We will not respond on the digital raised hand. For your knowledge, the webinars will be recorded, and after, when we have finished all the sessions, they will become available, including the presentations. And we also are working on the fact sheets for the 4 technologies which will be dealt during this seminar series, and they will become available as well. I would say enjoy. Ladies and gentlemen, we are in the middle of the heat transition, and in the heat transition, we are working on existing heat sources and new heat sources like geothermal, solar collectors. But the big challenge is that during summertime, we have a lot of surplus of heat, while during wintertime, we just need a lot of heat. And to cover this gap, we have some solutions like tank storage or pit storage, or we can use boreholes or aquifers. And in this 4 sessions, we will go and dive in more detail to the various solutions, and that's what we did in Task 39. We have described a few key objectives, and we have separated the work in 4 subtasks. And Wim van Helden, chairman of the Task 39, will go in much more detail, so you can read it afterwards in the PowerPoint. This is an overview of all the companies who joined in the Task 39. So most of them are companies or institutes or universities in Europe, but also from the US and Canada are companies present. The agenda for today: after the introduction, I will give the floor to Wim van Helden. And then we have a short Q&A session so you will be in a position to ask some questions to Wim about Task 39. And after that, Nico will tell you more about the high temperature ATES system. Then we have a Q&A session again, and I will close with some remarks and the program for the next sessions. The next sessions are presented here, but also at the end. So for today, task 39 on high temperature ATES is on the agenda. And next week, we will go into detail on the high temperature borehole thermal energy storage system. Then in December on the pit storage, and we will finish on the 14th of December with tank storage. For now, thank you very much. I will give the floor to Wim van Helden. Wim van Helden studied technical physics at the Technical University of Eindhoven in the Netherlands. And since 2014, he works with EEA Intec in Austria, an independent research and development institute. His working area is both compact and large thermal energy storage technologies. He is task manager of the IEA Energy Storage Task 39 on large thermal energy storage for district heating, and is coordinator of the EU-funded project Treasure that will start next year and is aimed at demonstrating 7 pit storage techniques in 5 European countries. Next to his work, he is also an independent consultant for renewable energy with a focus on solar thermal and thermal storage technology. Wim, I give the floor to you.
Thank you, Bas, for the introduction. You will hear in the next 15 minutes more on task 39. The title of this task is Large Thermal Energy Storage for District Heating. It's a task that has been running since 3 years now. It will end in December. And in the next 15 minutes, you will see some of the background of large thermal energy storage, how the task is structured, and some examples of the outcomes of the task. Then also a short introduction to the thermal energy storage project that Bas mentioned, the Treasure project. So why do we need large thermal energy storage? It enables more flexibility in district heating system, but also in industrial heating systems by connecting several sources for heat in the system, like solar thermal, as was introduced already, for seasonal storage, also industrial waste heat or geothermal heat, and other sources. Next to this flexibility, it also enables 100% renewable district heating by gathering all the renewable heat that can be harvested throughout a year. So for district heatings to become 100% renewable, it's necessary for these systems to also have large thermal energy storage. So this is an enabler for 100% renewable heated district heating systems. In task 39, we addressed 4 ATES technologies depicted here. Tank thermal energy storage, in which the tank structure above or underneath the surface will serve as a water reservoir in which heat is stored. Thermal energy storage, in which it is dug into the ground, and then the earth that is coming from the ground is used to have a dam outside as a cover on top of the pit to insulate it, and the pits normally are filled with tens of thousands of cubic meters of water. Then we have the borehole thermal energy storage, in which a series of boreholes is drilled into the ground, and then with a closed loop system extracts heat from the ground to be used either with or without a heat pump for heating purposes. And then we have aquifer thermal energy storage, in which a ground layer underneath that is carrying groundwater is used to store heat at different depths possible. So we work with technologies that either use water or soil as a storage medium, We look at applications into district heating or in industry, and we look at different time periods in which the heat is stored, either seasonal, daily, or multifunctional. An important aspect is also to bring this technology and its application possibilities also into the attention of policymakers. And that is also why we, in this task, have a separate subtask on the dissemination actions. There's the potential of thermal energy storages. For the Treasure project, we made a first assessment of the potential for Europe, and it is based on the total district heating final energy consumption, which is in 2018 440 terawatt hours. We assumed that 40% of the ATES technologies would be covered by thermal energy technologies, and that 30% of this annual heat demand is needed to be stored in an ATES. Then we come at a presently needed ATES capacity of about 54 terawatt hours, so 54,000 gigawatt hours. And in 2050, we expect that there will be fourfold growth of this demand, coming to this figure here, 220,000 gigawatt hours, which is a gigantic number. It's a very large number. We are talking about large thermal energy storage. So what is the definition of large? That are storages that contain at least 1 gigawatt hour of heat per year, either in several cycles or in one cycle. And that the store heat also should be suitable for discharge into district heating networks, meaning that there is a temperature between 50 and 100 degrees centigrade stored. So how is the work in an IEA task organized? In principle, it's a collaboration of experts that are independent of each other, work on a common work plan, and they all have to bring their own finances, their own funding in order to do the work that is meant to be done in the task. So when starting with the work plan, there's a kickoff meeting, and then every 6 months we have an experts meeting. We started with task 39 in October 2020, and there were also several technical tours that we connected to visits. In the Aalborg meeting, we went to the Dronninglund pit thermal storage. On the left, you see here a picture of the group standing on the floating lid of the storage. And 6 months later in Hamburg, we went to Meeldorf to see the thermal energy storage under construction. And in the background, in the middle photo, you see that there is still not yet cover at that time over the storage. We were there at the moment that the first parts of the lid were being constructed. How's the task organized? We have 4 subtasks. Subtask A is on working on the application scenarios, assessment of concepts and integration aspects. We have a subtask B on components and on materials database. We have a subtask C on the numerical simulation and how to compare the different simulation software with each other through a round robin. And subtask D collects all the knowledge that has been generated and then makes them ready for dissemination towards decision makers. In the next 4 slides, you see some examples of work and deliverables that have been produced by the subtasks. For example, for subtask A is a list of key performance indicators, KPIs. What we did, we made a long list of possible KPIs on 3 different levels: on a technical level, on an economic level, and on an environmental level. And for these KPIs, we made, if possible, definitions of the KPI, how to measure them, and what are the lacking aspects of a KPI and what to look for when calculating or when determining the KPI. Going to subtask B. Subtask B was working on the materials database and also on material tests, procedures. An example of the database is given here, the structure. First, there's a technology selection. You can either use pit storages or borehole or aquifer or thermal energy storage. There's a component selection for every technology. In this case, the components for storages are soil, the protection layer, the tightness layer, water itself, and the thermal insulation. And then for every component, you can select the different materials that are being applied for this component. And then for each material, the different technical specifications or physical parameters have been listed in order to give people the possibility to make calculations with material. Going to subtask C, round robin simulation. In the task, a lot of institutes in parallel produced simulations, numerical simulations, for a simplified load profile. We call it stage 1. The simplified load profile means that there is a charging period of 3 months every year. And it's a 3-month waiting, and then it's a discharging of 3 months. And we calculated the performance of the storage for 7 cases, 2 tank thermal energy storage cases, 2 cases, 1 ATES and 1 BTES. You see here in the right column that in total there's a large number of participants calculating the different models in the different configurations. What we did is the task compared the different calculations and looked for the causes of differences that were in the calculation. At the end, we arrive at a procedure and boundary conditions in which the different states will be calculated, and that guarantee then highest possible identification of the different models with each other. In subtask D, we work on the knowledge base for the decision makers. We make leaflets and information material in general. Material will be ready end of this year. And we have the task 39 webinar, this one. And we will have a policy workshop on the 5th of December. It will be an online workshop, trying to answer the question whether large thermal energy storage are a key element of the future energy system, addressing what the barriers and challenges are for bringing these technologies into the market, and especially aimed at policy and decision makers. We have a panel of National Energy Agency from 4 different countries and from the European Commission. And we have task 39 experts. We will have introductions on the different questions regarding ATES and the discussion on the challenges and the barriers. Some examples of the leaflets that we produced. We have leaflets on the use cases, but also technology descriptions. This is a use case of the tank thermal energy storage that has been built by Vattenfall in Berlin. It's a 56,000 cubic meter large storage. You see it here in the picture, still filled with water at that moment. And it's used by Vattenfall Wärme Berlin to be, a flexible element in the district heating networks of the city of Berlin in Germany. Another example, which you will hear more of in the next presentation, is the aquifer thermal energy storage. There's first a technology summary and then another leaflet on the use cases. In this case, for the high temperature ATES that will be also handled by the next presenter, by Nico. So let's dive further into what the future is for task 39, we just got the green light to have a follow-up task. It will be task 45 for the energy storage program. We will build further on the work that has been done on task 39. And the title of it, the 45, is Accelerating the Uptake of Large Thermal Energy Storages, because we have a shift towards opening up markets for large thermal energy storage. So the work that we will done is more aimed at opening up these large markets, working on standards, working on preparations for the performance guarantees for thermal energy storage, and a lot more of actions. It has a 4-year duration, and it will start the 1st of January next year. And already we have 22 organizations from 7 countries that will participate in this task. A bit more about thermal energy storage. ATES is an example of one of the thermal energy storage, at the moment the biggest in Denmark, 200,000 cubic meter in Voyens. And we will start a project, a European funded project called Treasure. It's about demonstrating and accelerating the uptake of thermal energy storage. You see here in the map of Europe the different locations in which we have 7 demonstrators planned. Blue square here is Høje Dastrup. It's an already existing thermal energy storage in Denmark that will serve as a reference and monitoring PTES. The other 7 demonstrators have a different stage of realization. Some are still in planning, other are in the building phase. And the idea is that through collaborating between the 7 demonstrators, we will have an acceleration of the, say, the time between planning and operation of thermal energy storage. Next to this, we have also 15 satellite initiatives that look over our shoulders and that we also have workshops with in order to also let them profit from the technology development and the process development that will be done in the project. So that was all about Task 39 and the Treasure project as an introduction. There are some references that you also can go through and see and read more on the large thermal and thermal energy storages. And with that, I thank you for your for listening to me. Thank you.
Thank you very much, Wim. Very clear presentation and good introduction to the Task 39. I hope now we have a better idea of what we did during the last years, and we have a small introduction to the results. There's time for a few minutes questions. David, do you have one to bring up?
Yeah, I have a few questions, few technical questions as well. One broad one by Els, which came in, is about a bit broader speaking. What is the difference? Why is there a difference between countries with regards to why some thermal energy storages are applied or are much further in some countries than others? That's maybe a bit of a general question, but could you shed a little bit of light on that, Wim?
Yeah, there are 2 factors that determine whether large thermal energy storage, or in this case the pits, are being applied in the country. One is the presence of district heating system and the structure of financing for these district heating systems. Denmark has a large number of pits because already 15 or 20 years ago, the Danish government decided to have higher taxes on gas for heat generation, meaning that there was an incentive for district heating operators to have solar thermal. And for solar thermal, you would need a pit thermal energy storage. The other determining aspect is the composition of the soil, so the geology of the soil. And pit thermal energy storage are best built and or also cheapest if the groundwater is very low. So if you don't have trouble when digging a hole that no groundwater is coming up, then the building costs are much lower. And that is these are the two main reasons that in the Netherlands, the pit thermal energy storage until now have not yet been realized.
All right, good. Thanks. And also thanks for that connection to the Netherlands as well, and at the last bit there. Also a question from someone. Can you say something roughly about sort of differences in heat losses between systems? Are they comparable? Are there what are we looking at here?
Yeah, in general, one can say if the system is bigger, then the heat losses are lower. And I can give an example for pits. If you have a pit thermal energy storage that has a weekly operation, so charging, discharging in 1 week, then the the losses are as low as 10% or less. So there's an efficiency of 90%. If you go to seasonal storage for a large thermal energy storage, so say 100,000 cubic meters, it will be in the range of, say, between 75 and 85% efficiency. And the numbers for ATES, I think they will be mentioned later on.
Right. That sounds good.
Maybe just one small question, David, and then we go to the next speaker.
Right. At least, I don't know, we can make it as small as we want, but I think it might be an interesting one for the, also considering there are quite some Dutch people in the crowd. Are there storage technologies which you would say that the Netherlands is leader in right now?
Yeah, definitely ATES. So if talking to foreigners, people from other countries about large thermal energy storage, then say the Netherlands are definitely world champion in ATES systems.
All right, cool.
That's perfect bridge to the next speaker.
Yeah, good one. Yeah,
So I would like to introduce Nico Franco Pinto. He's a mechanical engineer at IF Technology, consultant company in engineering shallow and deep geothermal energy systems. And Nico has designed many ATES systems and worked on the large-scale high-temperature ATES system in Middenmeer in the Netherlands. And this system has been designed from scratch and faced many complex mechanical challenges. But eventually, the system was completed in 2021 and is currently running smoothly. And Nico will tell you more about the high-temperature ATES system and its challenges. Nico, up to you.
Thank you very much, Bas. I'm sharing here the presentation. All right. So, as introduced, today I will be talking about the heat storage in aquifers, ATES systems, and in particular high temperature ATES systems. First, I will give a general idea of why is large energy storage important. I will go through that more quickly, being already touched upon that. Then I will explain what ATES is in general and why high temperature ATES, how is it different and why is it important? I will then explain how high temperature ATES can be applied, and finally I will talk about the steps necessary to go from to get a successful ATES system. So why is it actually important to have large energy heat storage? So space and water heating are basically half of the global energy use in buildings, and the other half being electricity. And nearly 2/3 of that energy still relies on fossil fuels. So there's a lot to be gained there. And the large energy storage will help to improve the business case for the sustainable heating technologies. And an important factor in this is that the price of heat storage per kilowatt hours is much lower than for electrical storage, which is very often the more talked about type of storage. Also, the impact on the environment is often significantly lower as electrical storage makes use of many materials, metals that have to be mined, that can also often be more difficult to recycle. So now about ATES specifically, aquifer thermal energy storage. As mentioned just now, is actually a very common technology in the Netherlands. In the world, there is around 40 or 4,000 systems, 3,500 of which would be in the Netherlands. And here we see the system of a standard ATES system. We have the cold water from the underground, which may be somewhere between 5 and 12 degrees. It's used to cool buildings during the summer, and the slightly warmer temperature of somewhere between 16 and 30 degrees will go into the warm well. This slightly higher temperature would then be used in the winter to feed some heat pumps and give the building some heating in a more efficient way. The most efficient part about the system is actually the cooling, because no heat pump, no other cooling systems are necessary. And this is actually very efficient, extremely efficient, and therefore cheap cooling. Wouldn't it be nice if we could do that with heating? Well, that's where high temperature and middle temperature systems come in. So right now, as we can see in the pie chart in the middle, the application is mainly for utility buildings, hospitals, greenhouses, and public buildings, because it's a relatively cheap form of cooling and air conditioning. But we see a small part residential. This part can significantly increase by applying middle temperature and high temperature ATES systems. There's a distinction there between middle temperature and high temperature, because there's quite a difference in complexity and costs between the middle temperatures up to 60 degrees Celsius and the high temperatures up to 90 degrees Celsius. The high temperature storage, that's what we will focus on now. So all the numbers that I will mention from this point on will refer to the higher cost, more complex high temperature storage. If it's any different, I will say that. So what is actually the main purpose of this type of storage? It's actually just to make other systems more useful. I could have said more flexible, more efficient, but actually useful covers most of what it actually does. The main uses would be for greenhouses and district heating systems. These have often a seasonal storage requirement or seasonal heating requirement more specifically. And that is ideal for thermal storage with ATES systems. Here on the right, we see the heat source, actually. That's a geothermal well. This geothermal well can produce heat for either district systems or for greenhouses. And it can produce continuous heat throughout the year. However, the demand is not the same throughout the year. In the summer, the demand will be lower than the supply that you have. Therefore, you can use the excess heat to store it in the underground in an ATES system. And this will also help improve the efficiency of your geothermal system by supplying cooler return water for the well of the geothermal well. And in the winter, instead of having to use a heat pump, very often you can just directly heat whatever delivery system you have behind your ATES system. And as said previously, this is a really efficient way of heating buildings. As long as your source is sustainable, you will be using more sustainable energy to heat up the buildings. So solar thermal energy is a very important one in this, because in combination with a large storage system like PTES, pit storage, or aquifer storage, It can provide a lot of heat in the summer when there's the most sun, and that same heat with some losses will be able to be delivered when it's needed in the winter. Another very interesting application is power to heat. And this is specifically because we also have big growth in sustainable electricity. If we have solar panels and wind turbines, these produce electricity at moments that it might not be needed. So to prevent the electricity grid from being overloaded, some of those turbines and solar panels might have to be turned off. Instead of doing that and not getting all the sustainable energy you could possibly get out of it, you can turn it into heat and store it in the underground and use it whenever necessary. So that's another very interesting application for thermal energy storage. Now I'm going to talk about a little bit in more detail about the integration of energy storage of ATES in a heating network. If we look at this picture, we have a geothermal well and another combustible source, often fossil fuels, and then the delivery systems to housing and here a swimming pool. You can notice at the temperature that the swimming pool actually needs a lower temperature. This is important. I will touch upon that in a bit. So first of all, in the summer, you have excess heat from your geothermal well. And then you can use that excess heat to load an ATES system. You can load it at a continuous temperature, let's say 85 degrees, as is in this example, for a whole season. And this whole season, in this case, is 21 gigawatt hours. Once you have a higher demand than the supply of the geothermal well, you can start using your ATES system. And something very important to note is that the temperature of an ATES system will reduce the more you extract water from it. The lower the extraction temperature you can have, the better, because then it means that you get more energy out of your ATES system, and the whole system will be more efficient. So in this case, for the integration, it would be ideal to be loading here at the highest temperature and supplying at the location where the lower temperatures are needed. Then you can extract as long as possible. Once you're done with that, once you go below temperatures that are not usable anymore for direct heating, you can also choose to heat up the return water for the fossil fuel installation. By doing that, for example, if your fossil fuels were providing 10 megawatts, you can choose to preheat the input with 3 megawatts of lower temperature ATES water, and thereby saving up 30% on the carbon emissions. Finally, you can also, once you cannot do this anymore, you can choose to couple it with a heat pump and deliver the heat directly onto the grid. That's a way to make the ATES system more efficient, but it comes, of course, with additional costs. So what are the main challenges for ATES systems? It's actually matching supply and demand. And it's about temperatures, power outputs, and energy. If we have a look at this graph here, we have a geothermal source that can provide continuous power and a lot of energy. But in the summer months, there's simply not that much demand. Instead of letting it stopping your geothermal wells, you can choose to keep them going and provide more heat, but instead to the ATES system. Those are the yellow bars at the bottom. Those can then be used in the winter to provide some sustainable heating to the systems behind it, and thereby reducing the combustible source, in this case, the green bars. The other main challenge for ATES systems is finding the suitable underground layers. So it's not possible to have ATES systems just anywhere. The Netherlands is particularly well suited for that, but definitely not the only place. There's many more places in the world that have similar underground compositions, and specifically around rivers with densely populated areas. Those could be potential good areas for ATES systems. How does the underground look? Actually, like a layer cake. And the ideal for an ATES system is to have, well, we have sandy layers and we have clay layers. But then you need a thick clay layer that separates one sandy layer from the other. Thereby, if you have the storage here, you won't have heat leaks to the layer above. Also, it's important to have a clay layer below. This prevents cold water from infiltrating from underneath, thereby having here your contained energy storage. Now, onto some more technical details and costs. So how flexible is this system? If we look at the controllability, actually quite flexible. You can go from 20% power to 100% in just 5 minutes. So you can go from, let's say, 1 megawatt of heat to 5 megawatts in those 5 minutes and back to 1 megawatt in the same 5 minutes. The scale of this storage, it could start for lower temperature systems, and that's a very important caveat, at 600 megawatt hours. And the high temperature storage that we have in Middenmeer has been designed for 38 gigawatt hours per season. Okay, so below 60 degrees Celsius, there are pumps that can use high frequency reversal, so they can turn on and off very frequently. This is the middle temperature range. That makes it also possible to do day-night cycles or weekly cycles. For higher temperatures, between 60 degrees and 90 degrees Celsius, this is still limited, but we are actually trying to develop systems right now that will be able to do more frequent switching between loading and unloading. So what timescales are important for ATES systems? First of all, the storage duration. You need seasonal storage. You need changes in seasonal supply and demand. And then another important timescale. If you have an original idea, how long will it take until you get the finalized product? Well, about 4 years, depending on how smooth the processes go. If legislation or other things are in the way, it could always take longer. And this other part about efficiency. We heard from Wim that some systems have just 10% losses. An ATES system, you should think more around 20% for the one in Middenmeer, for example. But that will only be achieved after 5 years, because in the beginning, your underground will be cool, and you need to preheat the sand in the underground, and that takes a while. That not just 1 season, after 5 seasons, it will be fully heated. This could be quicker at lower temperatures, and if you apply a heat pump, because with a heat pump, you can extract heat for a longer time and extract more of the heat out of the soil. You could possibly reach a 90% efficiency, and it could be achieved within 3 years. Then the expected lifetime of these systems. We don't expect a well-designed system to have 2 significant changes in the underground. So a lifetime of over 30 years should be possible. It's important to take good consideration in the design and make sure to keep monitoring the system well. But this is what we expect. Finally, the estimated costs. We expect between 2.5 and 4 million euros for a system with 2 wells for high temperature the one which is 38 megawatt hours. And then how big is it actually? If we look at the technical room, where you have all the connections to also the district heating or your greenhouses in this case, a surface area of 120 square meters is what you should take into account. This is for a system that has an initial power output of 10 megawatts. For water treatment, you will also need some space. This is always a separate space. It's about 40 square meters, and also the height is important. It will be about 5 meters high. And then what else do you see? What else is above ground? The well. We see here a lot of piping, a lot of connections, and this we want to simplify. And we have also a nitrogen tank to prevent corrosion of the metal right here. In the future, we want to make everything out of glass fiber reinforced epoxy like this part. And in that case, we wouldn't need nitrogen to prevent corrosion. This would also make it a bit smaller. Right now, it's 3 meters tall, 3 meters long, and 2 meters wide. In the future, that will be possibly 1 meter smaller in at least 2 of the dimensions. And what do we not see? That's what's on the ground. That's actual storage. And that's 600,000 cubic meters of water. So it's a big number. What does it mean? Here we have an Olympic swimming pool for scale, about 2.5 meters deep. And just take 200 of those. That's the scale we're looking at for high temperature ATES systems. This is how big it possibly could get. Now I'm going to tell more about the process that we go through to get from the original idea to actually having a working system. Something very important is the feasibility. It's not something you do just quickly, just a quick scan, but the whole feasibility process includes test drilling, for example, to know exactly where in the layer cake you have those nice underground layers. You also need to have the matching energies, the matching temperatures, and you make a general sketch of your rough design. Then you go on to the detailed design and permit. Well, I thought the permit is just a bunch of text, so here is a bunch of lines with the detailed design. It takes a lot of consideration initially when you are just building it up from scratch, but now we have a good example in Midemere, and for the next time we have a good base to work from. This design is then used to start the realization phase. We need to have good contact with the contractors, make sure everything is matching, everything is well planned, and to have a very good testing procedure in place, so you know that during the exploitation phase, you will have exactly what you need. Besides that, in design and permit phase, we also installed a lot of measurement equipment, which is also being very useful for the exploitation right now. The realization, here we see the building of the well. We're putting in the pump right there. It's actually a slightly larger footprint. This is specifically a system to put in not just a pump, but also to do maintenance. For the exploitation, we used measurement equipment we put already in the design to measure the temperatures, see how big our storage is in the underground, how the temperatures are. And we also measure the underground water to make sure that there's no significant differences and that we may be able to use the system for over 30 years. Finally, I will slightly touch upon the legal aspect of ATES systems. This is actually different for every country, but always important to conduct a complete research on the environmental influences. And that's got to do, for example, with drinking water. You don't want to drill near drinking water. You don't want to heat it up or possibly contaminated. It also has to do with other possible thermal energy storage systems that may be in the neighborhood. This is a large underground system, and there's other ATES systems or BTES, borehole systems, that might be affected if you don't take that into account. There's a lot of things to take into consideration before you can actually get a permit in the Netherlands. Different limitations will apply. So in the Netherlands, there's a permit available for up to 500 meters depth. If you want to go deeper, you go into different legislation, which is a bit more complicated here, but your mileage may vary in your country. Finally, the communication with the local residents is really important. Why? Well, obviously to avoid lawsuits, but also because actually you're creating something very special, very good to make the energy supply, the heating supply more sustainable. And that's something to be happy about. And if you design it well, if you conduct that thorough research on the influences on the environment, the technical risks are limited and the rewards will be high. So just keep in contact with all the different stakeholders. That's it from me. So I guess now it's on to the Q&A.
Thank you very much, Nico, for your very interesting presentation. You can see that it generates a lot of questions, which we tried to answer already a couple of them. I think it would be good to put some questions on the table, David. Which one would start with?
Maybe, I mean, I saw you also answering some questions, so feel free to address certain questions that you also saw as maybe some more trends. Thanks for the presentation, Nico. I think one question also came in about the sort of the ceiling temperature of ATES. What's the highest temperature that can be stored? And
oh, that's a very interesting question, actually. Currently, we have a design that works up to 90 degrees Celsius. So that's what we can say we can work towards, and we can definitely make. But there is definitely questions from the market to store higher temperatures, even up to 120 degrees. We have a lot of considerations maybe involving the underground. The mechanical part of it is actually, I think, doable. You can design around it, but the underground is something that needs more research on that. But it's certainly something we're looking into.
All right, cool. Yeah, thanks. Another question also came in after, I believe you mentioned something about the lifetime of 30 years for the borehole. People were wondering what's the process after that. Do you then add a new borehole, or how does that look, that future situation?
Okay, so like I said, it's 30 plus years. That's because we don't really have an upper limit on the amount of years that you can store energy. But it's more an estimate of what we think should definitely be possible. If for some reason after tens of years something happens that makes your storage not work, then it's possible to drill another storage, and you could continue using high temperature storage. It's not likely, I would say, if you design it well and if you keep monitoring it well.
Yeah. So the nuance there is it's 30 years plus. It can be longer than 30 if you design the system well.
Exactly.
Yeah.
David, I see also some people ask about the legal framework. I think that's a good question, because normally in the Netherlands, maybe I just answer by myself, that the rule is that you can store heat and cold between 5 and 25 degrees. That's regularly in the Netherlands, but there is a concept framework for permitting high temperature ATES systems, which has been designed with consultancy companies and a few provinces. to see can we allow large-scale heat storage, because they see that is a very relevant, they see the need also from the market and to implement district heating systems. So that's why they said, okay, we just allow it to do it, and also to check if the circumstances will be fine. And also many questions were related to what are the risks for the environment, for the microbiology, etc. And the interesting thing is that also TKI is supporting a 3 years research on the Middenmeer project, where we just look in much more detail to what was the initial situation, what is happening at the moment now we run the system, and what are the effects on the actual status and also on the long term. So that will help to evaluate the framework and to improve it, that it can be applied in all of the Netherlands.
Yeah. There were also a few questions regarding scaling. Could you reflect on that, Bas, or the current status of that?
Yeah,
Nico?
I'll elaborate on that. That's definitely a consideration. That's also why there's a separation between middle and high temperature storage. Actually, scaling is an important part of that. At 60 degrees, sometimes a little bit lower, but depending on your groundwater composition, you will get scaling if you do nothing. And in the past, there have been projects that failed because of that. So we do very close monitoring of the scaling, and we do some water treatment, which is adding a little bit of acidity. It can be either through carbon dioxide. That's what we are doing with the current system. It seems to be working really well. And it could also be with some other concentrated acids that you add to the groundwater. But it's for now, from what I see, I think carbon dioxide seems a really reasonable acid to add to the water.
All right. Interesting. And we have enough of that CO2, so
Absolutely.
Yeah, maybe one more thing that wasn't in the questions here, but I think is interesting. Could you also share a bit more on the potential of ATES for power to heat, or with regards to the rest of the electricity grid or the electricity system?
Yes. Well, maybe Bas, you could talk a bit about it.
It's quite interesting question, because we have designed the high temperature ATES system at Middenmeer with the purpose to store heat and just to be more flexible between geothermal and the greenhouse. But what we face is that they are also using it for, first, if they have a request for more electricity, then they can use CHP to generate electricity to balance the net congestion. And then they have a surplus of heat, and the surplus of heat can be stored in the high temperature ATES system. And there's also an idea that if there is too much electricity, that you convert it into heat and you can also store it. So we see there's a connection to balance the electricity network by using the high temperature ATES system. And it was not initially designed with that idea, but it appears up that the request from clients was, okay, is that possible? Yes, it's possible.
And we also have a very practical example of a location where they said, we simply cannot get a bigger electricity connection. We need to work more efficiently with what we have. And we cannot put all our sustainable energy back into the grid. So what do? You need to store it in some way. Batteries happen to be just too expensive. That's why they're now looking into high temperature ATES systems.
Yeah, thank you very much. Also, Dave, I think there are more questions. Maybe we can try to answer them later, but answering the questions, and they will be shared with everyone afterwards.
I think that's good. A few questions as well I pulled together, so some of them have also been answered while answering other questions, but we will look at that. Yes.
Just want to come to the closing. Just very good to know that next week we have invited Deep Kalantar and Julian Vormals to present more about high temperature BTES system, closed loop systems. On December 7th, we have 2 experts from Denmark, real hotspot for pit storage. Morten von Hobach and Jonas Sorensen will present. There is also another program on energy storage, which is another program than we have, but also on the 14th, just 1 hour prior to our meeting. So maybe if you are interested, you can join that as well. And then from 3 o'clock, we will have Ruud van der Bos and Geoffrey Chouchier to present more about tank storage. For now, if you have any questions about the program itself, the TCP program, then you can reach out to Stan van den Broek of RVO. His email is on the screen. And I would like to thank all the speakers for today, David for supporting with the Q&A session, and also, of course, all the people who joined the session. We were really happy that so many people joined this session, and we hope to see you next week again. Thank you very much. Goodbye.
Thank you.
Thank you.